Hello again, ladies and gentlemen. Now we're going to do the following example. Oops. This is the standard normal example 2 rather, not 1. Okay. Let's read it together. What is the area under the standard normal that lies to the right of 2.5? Okay. Yes. That is our question. Okay. As I've mentioned before, we're going to draw that first. We're going to draw our standard normal curve, and it looks like this. Okay. Okay. And we know that the standard normal is the normal distribution that has mean 0 and standard deviation 1, and therefore what lies exactly in the middle? The mean. And what is the mean? 0. So it's going to be right here. Okay. Okay. And the question is, what is the area under the standard normal that lies to the right of 2.5? So where is 2.5 relative to this? It'll be over here somewhere, right? Okay. 2.5. Okay. So if I draw my vertical line there and I ask, what is the area they want me to calculate? What is the area that lies to the right of it, right? So it's not this one, because that lies to the left of it. So it's this part. It's the tail, right? Okay. So now, again, we can, even though this is not part of the problem, we could attach to this area a probabilistic interpretation. Okay, so let's do that right away. So we could interpret it, even though that's not part of the problem, but I want to give this to you, because it's important. If we had an experiment that was modeled by the standard normal, this area, okay, this area that's shaded here could represent the probability that the experiment took on a value in excess of 2.5, okay? Or in other words, the probability that the standard normal takes on a value that is greater than 2.5. Okay? Okay. So now the question must be, to get to the heart of the matter, to solve the problem, what is the area under the curve to the right of 2.5? Well, again, I'm going to ask you all to pull out your magical standard normal table. No, I'm just kidding. Your cumulative standard normal table, okay? And what we see right away is this. If we look at our picture in our table, we know that the table tells us the area to the left of a particular value of the standard normal, right? Here, we want the value to the right. But this is where, this is why it's so important to know that the area under the whole curve is 1, okay? Because if we know that the area under the whole standard normal curve is 1, and we can find out what is the area to the left of 2.5, then we can subtract those. And we can be left with this tail area. And that's exactly what we're going to do. So visually, okay? So visually, the way I want you to think about this calculation is as follows. I want you to imagine that I'm going to take the area of the whole curve, okay? Right? The whole thing is shaded. Everything, right? What is that? Well, that has area 1, right? We talked about that in the first lecture, okay? And we're going to take away from that the area that lies to the left of 2.5, okay? So let's say this is 2.5. My table, my standard normal table, will let me calculate the area to the left of 2.5, okay? And I encourage you to look at the table with me, okay? Put this down here, okay? So if we go over here in the table, we go to 2.5, we see that the area there is 0.9938, okay? 0.9938, okay. Right? Okay. So then, if I take 1 and I subtract 0.9938, what is that going to leave me? Look, so here, this is the whole area under the whole curve, and I'm taking away all of the area under the curve that goes behind 2.5. What does that leave me with? It leaves me with just the area to the right of 2.5, which is exactly what we want, right? Just the tail area. Let me fix this drawing a little bit. That's like too bad. Okay. Okay, perfect. Right? This is the area we want. And what will it be? Well, let's calculate that subtraction. Okay, so I want to subtract, so I want to do 1 minus 0.9938. Now, obviously here, this is going to require borrowing. But how am I going to do it? So here, if you want to imagine it, you can see this as like 10,000, right? Because I have 1 with 4 zeros. But how can I replace that? I can replace that 9,990 plus 10, right? So that's exactly what I'm going to do here. I'm going to replace the 1 with 0.999 and 10, because if you add 10 plus 9, that'll if I have 10, I leave the 0, I carry over the 1. The 1 plus 9 is 10, I leave the 0, carry the 1. 1 plus 9 is 10, I leave the 0, carry the 1. 1 plus 9 is 10, I leave the 0, I carry the 1, and I recover what we had originally here. Okay, now of course I said that I had 10,000. You guys know very well that I had just 1 here, but of course you can see that the same procedure works because of the decimal system. Okay, the way I could imagine it, in fact, is actually that I have 10,000 10,000s, right? If I have, in other words, just to be clear, I know this is kind of a little side note, but I want you to know how I justified what I just did. That if I have 10,000 of 1 over 10,000, 10,000 of these is exactly 1. So that's why this works. Anyway, let's proceed to the actual matter. And of course, if you guys had a calculator, you could just do it in the calculator. Now, it's true I don't want to encourage blind use of the calculator, but some use of the calculator is good, and especially in statistics, like it's almost impossible not to use a calculator or a spreadsheet or some other statistical software, especially in practical problems. Anyway, so now let's perform the subtraction. 10 minus 8, that's 2. 9 minus 3, that's 6. 9 minus 9 is 0. 9 minus 9 is 0. Then I bring my decimal point, and of course 0 minus 0 is 0. So I get left with this tail area, okay, being 0.0062. Okay. Now I've taken the liberty of using some technology here. And if you use technology to calculate this area, you will get 0.00620968, okay? And of course, you could probably get more decimal points after that, okay? If you needed more accuracy for that calculation, okay? The most important thing I want you to notice about this is that by drawing a careful figure and by doing the calculation visually with your table, it helps you to do it it helps you to develop intuition to solving these problems. And it also just helps you solve the problems. I know it looks like extra work, but it's worth it. Okay? Now, at this moment, I also want to remind you of something else. Because even though so we solved the problem. We already got the answer here. But I want to take this moment to solve it in an alternate way. Okay? And that is, I want to remind you about the symmetry properties of the normal curve, and I want to use the symmetry properties here. I want to exploit them so that we can solve this problem in a different way, okay? Well, I mean, so yeah. So let's do that. So let's do that together here, okay? So again, what's the answer to this problem? The answer is 0.006. Oops. Okay. Okay. So now, okay, let's continue. We don't need this anymore. Okay. 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 So now, if you recall our discussion of the symmetry of a normal curve, we know that if you go a certain distance from the mean, okay, if you go a certain distance from the mean to one direction, then the tail area to the right of, well, okay, so let's assume that you go a certain distance to the right of the mean. Then the area in the tail off to the right after that distance will be the same as the tail area if you go to the left by that same distance. In other words, one of the symmetry properties we saw earlier, okay, when we were discussing the symmetry of the normal distribution, is that if I have, for example, in this case, I have the mean is 0, right? And I'm going to the right 2.5, right? And what I really want is I want this area. Obviously, that's the picture of the area we want, right? This is the area we want. And what we said when we were talking about the symmetry is if I start in the middle and I go a certain amount to the right, then the area of the tail to further right from there will be equal to the tail area, okay? If I start in the middle, if I start at the mean again, and instead of going to the right, to the left, and I go further left.
This is the top result.
Excuse me about that. So, for example, here, if I go, okay, so again, let me just restate that here. If I go from the middle, the mean, to the right by a certain distance, then that tail area will be the same as the tail area if I go from the middle, the mean, to the left by the same distance in that tail, okay? Well, what does that mean? That means, in this case, if going to the right, I get the area, if going to the right, I go 2.5 units from 0, then going to the left by 2.5 units will land me at negative 2.5. And the symmetry property we talked about was that the area to the right of 2.5 will be the same as the area to the left of negative 2.5, okay? And now if you look at this, then aha, we don't have to do it like this, okay? We don't have to do any subtraction. We can say, aha, the area to the right of 2.5 has to be the area to the left of negative 2.5, okay? And so therefore, if I go straight to my table and I look at that over here, negative 2.5, aha, what is that? It is 0.0062, as it should be, because that's what we calculated earlier, okay? Okay? So in other words, we can answer our question again with the same quantity, right? This area is 0.0062. We got that straight off of the cumulative distribution table for the standard normal. And by symmetry, we know that that is exactly the same as the area to the right of 2.5, which is the area we were interested in. Okay? Okay. And there's finally one more topic that I wanted to cover once more. I kind of used it here, but I didn't make it explicit. But I'm looking at this as an opportunity to bring it back up because it's an important thing that I don't want you guys to lose sight of, and it is the so-called complement rule. Okay? When we were talking about probabilities, we know that if we have two events that together make up the whole space, the whole sample space, but that individually, but that they don't share anything in common, then you add them, you get 1. And so let me be specific here, okay? So for example, in our particular case, okay, the complement rule goes as follows. I know that the probability or not the probability, but we're going to interpret it as a probability, right? But the area to the left of 2.5, we know that that area, okay, plus the area to the right of 2.5, okay? Those areas have to add up to 1, okay? They add up to, essentially, the whole normal curve. I'm sorry, these are so small, but I know you guys get the picture. And from this, we know that, for example, 1 will equal to the probability that z is, let's say, less than or equal to 2.5, okay, plus the area plus the probability that z is bigger than 2.5, okay. And so if I look at it from this perspective, so here again, what am I doing here? I'm bringing back, or I'm reviewing the complement rule, okay, because I don't want you guys to forget this, okay. So I can interpret this like visual drawing in the following way. The area under this curve is 1. The area under this curve corresponds to the probability that the standard normal will achieve a value that's less than or equal to 2.5, and that one is the probability that the standard normal will achieve a value that is greater than 2.5, or that some experiment, properly speaking, that some experiment that is modeled as a standard normal random variable will take on a value that's greater than 2.5, okay? But what does this tell us? This gives us exactly, if I subtract this to the other side, I get that the probability, okay, that z is greater than 2.5 is equal to 1 minus the probability that z is less than or equal to 2.5. And that's exactly the complement rule, right? That if we have two events that together constitute all the possibilities, you can see that there's no possibility that is not covered by these two possibilities. Any possible value that the standard normal can take, which is any real number, is does satisfy one of these inequalities. So these two inequalities capture the whole space. So this is exactly the complement rule applied to this problem. Well, this is the one we're looking for, the area to the right of 2.5 under the standard normal curve, and it is exactly equal to 1 minus the probability of z to the left of the standard normal curve. To the left of 2.5 under the standard normal curve. And you can see that this is exactly what we did visually. So here, this argument looks a lot more complicated, but it boils down to what we did visually here, right? Because if I draw the pictures for this one, I'm saying that this one, which corresponds to the area to the right, which is what we want, right? To the right of 2.5 under the normal curve, is equal to the area of the whole normal curve, which is 1, okay? Minus the area to the left of 2.5 under the standard normal curve. And of course, you can see that that is exactly the way we did it originally, but I wanted to take this opportunity to show you how what we did visually was just an application of the complement rule. Okay, just to recap, we solved it first visually. I want you guys to draw the pictures because that'll help you to learn that. Number 2, I wanted to show you how symmetry can play a role in solving these problems. Okay, and so that you can see what symmetry means here. And finally, I wanted to remind you of how our visual technique is just an application of the complement rule, as you see here. And I wanted also show you this further enrichment, okay? Now, if the symmetry argument and the complement rule were confusing, don't worry about it. Follow the visual technique. Later on, you can understand the complement rule application, or how it's an application of the complement rule, the visual technique we did earlier. And also, with time, you can also understand the symmetry argument. If you understood it all, that's also great. And in any case, I hope you've enjoyed this, and I look forward to seeing you again soon. Thank you so much.